Hello and welcome to Lab 2, Motion of a Falling Object. So before we begin, we have to go over some concepts that will help us later in the experiment. So we have Newton's second law, which is the momentum principle. This is the net force is equal to the change in momentum over the change in time. And from this law, we can derive the velocity and position update formula, which we will be using later. Then we have two forces that act upon a falling object, which is the weight force and the drag force. The weight force, or otherwise known as gravity, is equal to mass times the gravitational constant, which is 9.8, in the negative y direction. And then we have the drag force, which is equal to the proportionality constant times velocity squared in the opposite direction that velocity is going, so the negative v hat. And then we have the net force, which is our weight force plus our drag force on this falling object. So first, we are going to observe the falling object using tracker, and then we're going to create a computational model using GlowScript with only gravity acting on the falling object. Then we're going to create another computational model, but add drag as well as gravity. Afterwards, we're going to create a graph plotting all three of these position versus time coordinates and compare them. And lastly, we're going to answer some what if and why questions. So first, I observed a paper ball falling. I imported the video, cropped it, and assigned length and coordinate axis. And as it falls, I collected position versus time data points that you can see on the right hand of the video. So we got the start and end time, the initial position. The initial velocity can be considered 0 since it's starting at rest. And based on this data, I began to construct the two computational models using GlowScript. So first, we have the gravity only one. So here is the code. I had to input the ball's mass, the initial position, the initial velocity, time, the gravitational constant, and no proportionality constant since we are not doing drag, the ending time, and then the net force, which is just the weight force. So that's the negative mass times the gravitational constant, 9.8. And of course, the velocity and position update formula. So here, if we run it, you can see the net force, which is just the weight force, pointing downwards. And we get our position versus time graph. This makes sense. We're going in the negative y direction. And then if we scroll down, we get the rest of our coordinates and the velocity versus time graph. So now we're going to add drag. Everything mainly stays the same, except for the proportionality constant, which is 0.00899. This was found by just guessing and checking and seeing whenever the final position matched up with the tracker's final position, and that's how I got the proportionality constant. We also had to add in the drag force to our net force, so that's, of course, the formula we discussed in the introductory slide. And here it is when we run the program. So we have the weight force pointing down, and then we have the drag force going up, so opposite the motion of the ball. Here we have the position versus time graph, and then if we scroll down, we'll have the velocity and all the coordinates that we will use to compare. So finally, we can plot all three on the same plane to actually see what's happening. So we have our observed from tracker in blue, our predicted with gravity only in orange, and our predicted with gravity and drag in gray. As we can see, the gravity only prediction is completely inaccurate. It has the object falling much faster and further, and then the predicted with drag is the closest to the observed. So what does this all mean? Which models, if any, predict the terminal velocity? So a terminal velocity is when the force of drag has exactly balanced out the force of gravity, which means the net force is 0, causing constant velocity. So without drag, it does not reach it because there is no drag, and then with drag, it does. And what if? Imagine the object was initially thrown downward. Would the terminal velocity be the same? And yes, it would. So I created a model with a initial velocity being thrown downwards, and terminal velocity is still reached because the initial velocity is irrelevant when talking about terminal. Thanks for watching.